All right, geometry, lesson 51. It's good to be back. Properties of isosceles and equilateral triangles. Well, let's just start with our title there so far. Isosceles triangles, what are those? Triangles with two equal sides, good. Equilateral triangles, triangles with three or all equal sides, right? All right, and of course, these are classified by their position in relation to the triangle's congruent sides. The sides and angles of the triangles are classified by their position in relation to the triangle's congruent sides. So the first little label that we have here is the leg of an isosceles triangle is one of the two congruent sides. So can anybody point out to me using two letters, right? Because we can't identify a side with only one letter, right? We can identify an angle with only one letter, but we need two letters to identify a side. Can we give me two letters that identify a leg of the triangle shown here? A leg, based upon the definition. Yeah. AC. Yep. AC is a leg. And I will say, super excited. We got a new bulb in our projector, so we can see now. So it's real sharp, and crisp, and clean. Okay. Another leg. Somebody else. Okay, Maddie? AB. AB is our other leg. Okay? So an isosceles triangle is going to have three legs. Or not three. Isosceles triangle is going to have two legs. I was telling somebody the other day, I was like, I hope I remember how to actually do this. So, I mean, in terms of being able to teach. So in the diagram, we see AB and AC are the legs. So if you didn't know already, all you really had to do was go ahead and read. But hopefully we knew the answer even without reading. All right, so let's look down here. The next little label that we get is the vertex angle of an isosceles triangle. Is the angle formed by the legs of the triangle. So in all of this, what should be our vertex angle? Angle what? Somebody who's not Chandler, not Maddie? Angle A. Okay? This is our base angle. It's different than our base. Our base is our side that's opposite the vertex, right? Or I'm sorry, I wrote base angle. It should be our vertex angle. Okay? So vertex angle is the angle formed by the legs of the triangle. The vertex angle there is angle A. Base of an isosceles triangle is the side opposite the vertex angle. So it's the only side that's left here, which is BC. Okay? All right, do we understand the labels here? Okay, great. So we should be able to identify the legs, the vertex angle, and the base of an isosceles triangle. Okay? All right, now we'll get into some actual theorems based upon isosceles triangle. If a triangle is isosceles, then it also has something that are called base angles. Okay, base angles. Now, your base angles are at the base of your isosceles triangle. All right, what is the base of this isosceles triangle using two letters? Maddie? MN, very good. So if this is my base in terms of sides, then what are my base angles, Jose? Angle M and angle N, very good. Now, what you'll also notice about the base angles of an isosceles triangle is that they are always the angles that are opposite the two congruent sides. Okay, so if we see those tick marks, we're going to find the angles that are opposite of those. Those are always going to be my base angles. And the reason I bring that up is because we could take this triangle here, and sometimes, you know, I mean, if we rotate things around, it can get a little bit trickier to see. You know, I can move my tick marks around and all that kind of different thing, right? You need to be able to find the base angles, be able to find the vertex angle, be able to find all that stuff, no matter what the rotation or orientation is. Okay? So it's going to be in relation to our congruent sides. Does that make sense? Everything is in relation to our congruent sides. So angle M is congruent to angle N. Very good. Okay. Then we have something that's corollary. It's in relation to the theorem that we just got. If a triangle is equilateral, then it is equiangular. Okay. That really kind of should be a big no duh, right? We know at this point when dealing with triangles that if it's equilateral, it's equiangular. Now that's not necessarily always true of other things, okay? But in triangles it is true. If it's equilateral, it's equiangular. All right. The converse of the isosceles triangle theorem is also true, as is the converse of corollary 51-1-1, meaning converse means is where I flip the hypothesis and a conclusion, correct? So basically what that's saying is that the converse of our corollary up here is true. If a triangle is equiangular, then it is equilateral. All right, we'll even go back and let's see what the converse of our previous theorem is. If a triangle is isosceles, then its base angles are congruent. What would be the converse of that statement? Flip the hypothesis and a conclusion. If a triangle's base angles are congruent, then a triangle is isosceles. Okay? All right, so if I see something where I got something like this, where I see these two angles are congruent to each other, then I know that this triangle is isosceles. I could go ahead and write in, then those two things are equal to each other. Okay? If this was 30 degrees and this was 30 degrees, then the sides opposite those two 30-degree angles have to be the same length. Okay? All right, so this represents the converse here. All right, 51-2, converse of the isosceles triangle theorem. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. Okay, that's kind of what we were just looking at in terms of those base angles. Okay, if a triangle is equiangular, then it's equilateral. We've established that. Okay, 51-3, if a line bisects the vertex angle of an isosceles triangle, then it is the perpendicular bisector of the base. All right, so let's go ahead and draw something like that. All right, I've got a triangle here. Let's see. We'll go ahead and make this isosceles with the easiest orientation that we can come up with. All right, where's my, let's see, let's label it so it's a little bit easier. We got A, B, C. Which angle is my vertex angle based upon this information? Angle B is the vertex angle. If a line bisects that angle, what does it mean to bisect something? Divided it into two equal parts, right? So I could create a line. It bisects that. Okay, so we'll say, okay, it's bisected. Then it is a perpendicular bisector of the base. So I know two things. Let's go ahead and call this D. What does BD do to AC? What does the line BD do to AC? It's perpendicular. So what could I draw in here to represent that it's perpendicular? How can I represent that visually? No? How do I represent two lines being perpendicular to each other visually? Okay, to show that two line segments are equal to each other, we use tick marks, right? To show that two angles are congruent to each other, we use these kinds of tick marks. To show that two lines are parallel to each other, we use two parallel lines. How do I show that two lines are perpendicular to each other? What's my right angle mark? The square. Okay. That's where we're... Okay, so we have that, right? We could write that in there. What else? Not only are they perpendicular, but what does BD do to AC? bisects it. So it does what to it? Divides it into two equal parts. So what do I know about AD and DC? They equal each other. Okay? So I want you to be able to do this, though, right? We took all the different parts, right? We made an isosceles triangle. We found out where the vertex was. We made an angle bisector, and then we took everything that we knew about it, and we're able to make a complete picture here. Okay? All right, let's look at something else. If a line is the perpendicular bisector of the base of an isosceles triangle, then it bisects the vertex angle. These two things are converses of each other. This says if this green line divides that vertex angle into two congruent parts, then it does everything that we see down here. All right? Theorem 51-4 says if we see everything that's happening down here happen, then we know that it's divided that vertex angle into two congruent angles. Does that make sense? Okay. All right. All right, we get something like this. The diagram illustrates both of those theorems. The altitude segment TU bisects the vertex angle. It's perpendicular to the bisector of the base of the triangle. All right, and that's it for those notes. Okay, let's see if we can answer a couple questions. Let's come down here. Okay. We have an isosceles triangle here. The orientation's a little bit different. What is the vertex angle here? Maddie? 42 degrees. All right. Which makes H what kind of angle in an isosceles triangle? There's a vertex angle, and then there are two base angles. What do we know about the base angles of an isosceles triangle? They're congruent to each other, right? They're equal to each other. So really, how many degrees are there in a triangle, every triangle? 180 degrees. So we could say 42 plus H equals 180, right? Because we know that this angle is going to be the same as that angle because they're opposite the two congruent sides, so they're equal to each other, right? You could simplify that. You could say 42 plus 2H equals 180, correct? Right? Now what would we do to solve for H? Subtract 42 from both sides, and then divide by 2. So we got 2H equals, what, 138? Something like that. What's 138 divided by 2? Okay. Work for you guys? Okay. Okay. This one takes things a step further. Okay. Meaning we need to look at what we know about parallel lines, what we know about adjacent angles, supplementary pairs, that kind of thing. We want to know what angles 1, 2, and 3 are going to be. Okay, so we have two parallel lines cut by a transversal. Okay, I'm going to challenge you on some of your lesson 12 stuff. Does anybody know what the relationship between 117 degrees and angle 3 is? If I have two parallel lines cut by a transversal, same side interior angles, absolutely. What do we know about same side interior angles? They are supplementary, which means they add up to 180. So if I wanted to know what angle 3 is, what do I do? 180 minus 117. What's 180 minus 117? 63 degrees. Okay, now keep in mind I still have two parallel lines cut by a transversal. What do we know about the relationship between angle 3 and angle 2? How do you know? What is it? What are they to each other? There's a phrase. No, they're not vertical angles. They're not corresponding angles. You are at least in the right chapter, but you're not at all talking about the right things. All right, look. We have two parallel lines cut by a transversal. What is the relationship between that angle and that angle? Except we don't say opposite, we say things that are on the opposite sides of the transversal are referred to as alternate interior angles. What do we know about alternate interior angles? They are congruent. So if angle 3 is 63 degrees, what is angle 2? 63 degrees. Now, we could have found that just simply on its own because 117 and angle 2 are also linear pairs, right? They form a straight line. So I could have found angle 2 the same way I found angle 3. Taking 117 from 180, I would still get 63 degrees, correct? Okay. Now, in this triangle, what is angle 2? What kind of triangle is that? It's an isosceles triangle. There's only two types of angles in an isosceles triangle. What type is angle 2? What are the two types of angles in an isosceles triangle? Try to keep in mind that I'm going to try to ask you questions that are based upon information I gave you like 10 minutes ago. There are only two types of angles in an isosceles triangle. What are the two types of angles that we know? Base angle and vertex angle. Is angle 2 base or vertex? Base. Okay? What is, and we need to solve for angle 1 though, right? Okay? How can I solve for angle 1 if I know that angle 2 is a base angle? Subtract 180. Subtract 180 from what? I'm going to subtract 180 from 63. That's going to give me a negative number, right? Add 63 again. Why? Why am I adding 63 again? So what you're referring to is the other base angle, right? So this base angle is also 63 degrees, correct? So you're saying add those two things to each other? All right, what is 63 and 63? 126 degrees, all right? How's that getting me any closer to angle 1? 180 degrees minus 126, right? Because there's only 180 degrees in this triangle. I know that there's 126 already spoken for. So what's 180 minus 126? 54 degrees. All right, you're going to see some stuff like this on a test. Okay? Do you understand why I made such a big deal out of lesson 12 when we came to it? Right? I told you were going to get it again and again and again, and it just wasn't ever going to go away. Right? Some of you need to go back to lesson 12 and watch the video, read the chapter, go over the lesson, you know, those types of things, because it hasn't gone away. It's popping up again and again, especially with having, you know, 2 weeks off of school. Even if you knew that stuff, you probably still need to review it to a certain extent. All right. Let's see. Let's take a couple minutes here. Let's see if there are, what, you guys had 2 through 30 even, right? Let me see if I can find, let's see, look at question 10. Okay, question 10 in your book, because this is a question that's in your homework. It says, it shows you a picture here. Explain why each angle of an equilateral triangle measures 60 degrees. Oh, you're not using the picture there. It's just a straight up question. Why does each, this is going to be something where you have to sit down and actually write sentences. Okay? So I'm going to look at this question, right? And if you just show me math with no explanation, 0 on your paper. Okay? Go back, do it again. Think about it. Why is every angle in an what does it say? Equilateral triangle. Okay, so if I have a triangle that looks like this, why is it that every angle is 60 degrees? What? Because they're equal. Based upon what? I'm not going to, if I see a sentence that says because they're equal, it's going to be a 0, you get it handed back. Let's use the information from the lesson. What theorems, postulates, corollaries from this lesson are going to get me a little bit closer? Okay, what theorem is that? Okay, so theorem 51-1-1 says. Okay? Right? That's how you can start. Now, basically what it says is that if a triangle is equilateral, then it is equiangular. Is that right? Is that what it actually says? Read it for me. Theorem 51-1-1. What does it say? Then it is equiangular, right? If it's equilateral, then it's equiangular. Okay? So how do I apply that information? Because this shouldn't be the only sentence I write. Theorem 51-1-1 says, and I'm stating it, now I have to use that information. Therefore what? If I know that if it's equilateral, then it's equiangular, therefore all 3 angles are congruent, and there are how did I get to the number 60? Okay, so let's talk about 180. There are 180 degrees where? In most triangles? In all triangles? And 180 divided by 3 equals 60. Okay, therefore 63 times is 180, right? All 3 angles are congruent. You see how we can do this? It might take a little bit more work, but actually go back into the lesson and look at the theorems and the postulates. There is a reason that those are the first things that we go over, because every question I'm going to ask you throughout the lesson is going to be based upon the information I've already told you. Okay? I'm not going to ask you something that you shouldn't know. Okay? It's not like some of our SMART goals and benchmarks and things like that, where you see questions like, yeah, you haven't learned this yet. We're just kind of trying to see where you're at and where we want to try to get to. Okay, so try to pay attention at the beginning to apply that information to the questions that are being asked, not only by me, but what's in your book. Okay? All right. Do you guys have any other questions? All right, I'll give you guys some time to get started here. I'll walk around the room, try to help you out if I can. Okay?